So you might have assumed, oh, that's just a little system in nature that has very simple rules. I'm going to be, because I have a much more sophisticated brain, I'm going to be able to just jump ahead. And even though it took it a billion steps to figure out what's going to happen to it after a billion steps, I'm just going to be able to, write down a formula and in one fell swoop, so to speak, just say, here's what's going to happen. But this principle of computational equivalence says that's not the way things work, that in fact, the computational capabilities of my brain or my computer or whatever else are no greater than the computational capabilities of this system with its simple rules. And so what that means is I can't expect to jump ahead like that. I'm forced to basically just follow the whole sort of irreducible computational process that the system itself follows. And that leads to this idea of computational irreducibility, the idea that there are computational processes where you just have to follow each step to see what's going to happen. And that idea of computational irreducibility just has an amazing number of consequences, which it's taken me sort of decades to progressively understand what all these various consequences are, whether they're for how we think about AI ethics, how we think about free will and consciousness and so on, to things about what we can predict in science, to things about sort of how the fundamental physics is put together and so on. This idea of computational irreducibility is a really important idea. I'd always thought that the laws of physics are just something we're dealt. It's like, here are the laws of physics, be happy, so to speak, rather than that the laws of physics are necessary for observers like us. And what we're seeing is that there's this sort of second law, general relativity, quantum mechanics, they're all coming from the same place. They're all actually the same phenomenon at some level of this interplay between computational boundedness of the observer and computational irreducibility of the underlying system.
Hello, everybody, and welcome back to Series 4 of Chasing Consciousness. So today we have the difficult and yet beautiful topic of trying to model complex systems like nature and the universe computationally to get into, and how beyond a low level of complexity, all systems, no matter how complex, seem to be more or less equally unpredictable. We have a whole episode in this series on complexity theory in biology and in nature, but today we're going to be taking a more physics and computational slant, which will then lead us into the all-important artificial intelligence safety debate and how important AI can be in helping us solve the big scientific questions if we can get the safety question right. Now, another key element today is observer theory, because we have to take into account the perceptual limitations of our species' context and perspective if we want to understand how the laws of physics we've worked out from our environment are not and cannot be fixed and universal, but rather will always be perspective bound within a multitude of alternative branches of possible reality with alternative possible computational rules. We'll then be connecting this multi-computational approach to a reinterpretation of entropy and the second law of thermodynamics. Now, the fact that my guest today has been building on these ideas for over 40 years, creating computer language and AI solutions to map his deep, deep theories of computational physics makes him the ideal guest to unpack this for us. He is, of course, physicist, computer scientist, and tech entrepreneur Stephen Wolfram. In 1987, he left academia at Caltech and devoted himself to his computer science intuitions at his company, Wolfram Research. He's published many, many blog articles about his ideas and written many influential books, including A New Kind of Science, and more recently, A Project to Find a Fundamental Theory of Physics, Computer Modeling and Simulation of Dynamic Systems, and just out in 2023, The Second Law, about the mystery of entropy. Now, one of the most wonderful things about Stephen Wolfram is that despite his visionary insight into reality, he really loves to be in the moment with his thinking, engaging in Socratic dialogue, even with the general public on these live streams. Check those out. Staying open to perspectives other than his own, and allowing his old ideas to be updated if something comes up that contradicts them. Something which anyone who's been following this show knows that I think is the sign of a wise scientist. And given how quickly the fields of physics and computer science are evolving, I think his humility and conceptual flexibility gives us a fine example of how we should update how we do science as we go. But you'll see that it is actually a philosophical approach that comes directly out of his computational irreducibility theory, the one that got him started way back in the 80s. Needless to say, I cannot wait to get into this. So without further ado, let's go. Stephen Wolfram, welcome to Chasing Consciousness. Thank you for coming on the show. How are you?
I'm just fine. Looking forward to a chat here.
Now, Stephen, I love to start by finding out the first deep ideas that grip my guests when they were young kids, just starting to reflect on existence for the first time. And I know you were writing physics papers by the time you were 15, so I imagine you were quite an early starter. What sticks out as significant as you look back at some of the questions that seemed important when you were a kid?
Gosh, well, I got interested in physics when I was about 10 or 11 years old. And I was, I kind of wanted to understand how physics comes to be the way that it is, so to speak, and how our universe kind of why it works the way it does. But I don't think I thought that deeply about it at the time. I think at the time I was mostly just learning about, here's what we know about physics. This is what we can deduce about how the universe works. I think it took me many years, even decades later, I got sort of more and more interested in the foundations of the foundations of the foundations, so to speak. I don't think that was, I think I started at a much more practical level, and I've been kind of going to these more and more foundational levels as I've progressed, so to speak. I think the thing, well, I got interested in a thing called the second law of thermodynamics, the law of entropy increase, the kind of tendency of things to get more random. I happened to get pretty interested in that when I was 12 years old. And I think I finally figured out how that really works now, like 50 years later. And that's kind of satisfying, but it took 50 years to get to that point.
Well, you've got a new book out on that, The Second Law, which we're definitely going to be talking about in a short while, listeners. So, Stephen, because this is an educational program for lay science lovers like myself that tries to kind of demystify some of the most groundbreaking work in modern science, I need you just to bear with us for a short time at the start while we set the scene for the huge implications of your work and just maybe define a few terms that may be new to the listeners. So before we get on to your recent books, let's start with a few of those key ideas. Now, first of all, before we introduce computational equivalence, irreducibility, and observer theory one by one, as a way of introducing what your idea of a computational universe is, perhaps you could map out the 4 stages of the evolution of scientific models, starting from the structural, so what things are made of, through mathematical, so the equations that then made predictions, then into the 80s when you got on board, when it all went computational, so program code taking over what equations used to do, and then into the 2020s when you've taken it multi-computational. Give us that history.
Yeah, right. So, I mean, sort of the earliest stages of science that happened in antiquity, people were kind of asking a little bit like what I was saying. I was interested when I was a kid. You know, what's the universe made of? How is it? What are the building blocks for the universe? And the earliest kind of scientific descriptions were mostly just that. What are things made of? Not a lot about sort of how things work, more are things made of atoms? Are things continuous? Those kinds of questions. That was kind of, I would say, the sort of structural approach to science, which is where we're still at in many fields of science, in many areas of like life sciences and so on. It's really just what's there, rather than kind of, is there a big theory of how this works? But so that was kind of the earliest stages of science. The big thing that happened in the 1600s was the idea that one could use mathematics and mathematical equations to kind of describe the world. So one could say, not what one could start talking about, oh, the Earth is moving around the sun according to this equation, and we can work out a formula for where the Earth will be some number of years from now. That was kind of the thing that launched a lot of kind of the sort of big expansion of exact science, was this kind of idea of let's use math to study science. And that was kind of a dominant theme. It's kind of the way people assumed if you're doing science, you're going to write down equations, you're going to be doing calculations with mathematics and so on. That worked quite well, brought us a lot of modern science, modern engineering, and so on. I myself was interested in questions like, how do very complicated things happen in the natural world? And when you write down equations and so on, they're good at describing things that go in simple curves or make simple patterns and so on. They're not good at describing things like, I don't know, the shape of a snowflake or the kind of complicated random flow that you get in fluid turbulence, these kinds of things. They're not good at those types of things. And so I got interested in, was there a way to make a theory of those kinds of things too? And what I realized is that the mathematical approach to doing that isn't that there are different kinds of theories that you can make. And essentially the idea is, well, if you're going to make a theory of how things work, there better be some definite rule by which the thing operates. That rule might be a mathematical equation with integral signs and all those kinds of mathy things, or it might just be some rule that says if you have an array of black and white cells and this cell is next to that cell and so on, then at the next step, this cell is that color and so on. It might be something which is specified in what we might think of in modern terms as a computer program. So I got interested in kind of, can one describe the natural world using rules that one could express as programs rather than rules that one could necessarily express in mathematical terms? And so that led to the question of, okay, you have these programs. What's the theory of programs, so to speak? Just like we have mathematics and calculus and so on as kind of a theory of how mathematical kinds of things work, the interest that I had was, what can we say about sort of a theory of how things like programs work? And one of the things that I had the sort of fun of actually being able to do sort of for the first time was kind of take a computer as sort of the analog of a telescope and look not out into the sort of astronomical universe, but into the computational universe of possible programs and just say, what's out there in this computational universe of possible programs? And I had assumed that if I had a sufficiently simple program, then the behavior of the program, if I ran it, would be somehow correspondingly simple. The big surprise that I had in basically the beginning of the 1980s was that isn't true. You can have a very simple program, very simple rules, and when you apply those rules over and over again, the pattern of behavior you get is really complicated. Sufficiently complicated that when you first look at it, you'd say, this is just random. But in a sense, it isn't really random because there are definite rules. You're just following these rules over and over again, and this is the pattern you get. It's just that to us, it's complicated enough that it seems for all practical purposes random. So this, I would say the next big paradigm that I see in kind of how to make theories, models in science is this idea of using programs to make models for things. And sort of the big phenomenon there is this fact that even though the model may be simple, the behavior of the system is not simple. I mean, as is often the case in science, when people first started talking about equations as ways to, and mathematics as a way to approach science, everybody was very skeptical. That was in the 1600s. So by the time we get to the 1980s, that's like, of course, that's how it works. And if you say, well, what about other ways that it might work, like things based on rules and programs and so on? A certain reaction was, no, it couldn't possibly work that way. We know it works according to equations. But the thing that's happened in the last 30 or so years is there's been a really pretty major shift in the direction of thinking about modeling things in the world in terms of programs rather than in terms of equations. It's kind of a silent revolution in a sense that's happened, that if you look at kind of the way people make models of things that they want to make models of now, it'll typically be in terms of programs, not in terms of equations. And they're very different phenomena that are important when you're making models in terms of programs as opposed to equations. Now, you mentioned also kind of a fourth level of kind of thinking about science. Maybe we should talk about a bunch of other things before we get to that.
I was going to say, maybe the fourth one will leave just until we get these other concepts in. Out of interest, was there anybody, any trailblazer before you who really influenced you in those early years in the 80s?
Well, I mean, there was, a lot of the phenomena that I discovered had, in some ways, people had seen kind of hints of these phenomena before, but people hadn't kind of said there's a big thing to really understand. So they mostly said, oh, there's the system and it produces this kind of random noisy behavior. That's a nuisance. We want to concentrate on something else. And or other people saying, these are systems we could study and we kind of get stuck here. And the main sort of thing that I realized is those things that people said, oh, that's kind of a nuisance, or here's where we get stuck. Those are hints towards a big thing that I ended up writing this book called A New Kind of Science, which is kind of the title of the book, I think, is a pretty good description of what the kind of intellectual phenomenon that occurred there was. But no, it was, I mean, in a sense, the idea of computation, the idea that that you can specify rules for operating a machine like a computer, and that those rules can be used to do lots of things, that you can have a single kind of universal computer that can run different programs to do different operations. That's an idea that originated actually in the 1920s and 1930s. People started to understand it a bit better by the end of the 1930s. And that was sort of an important precursor to the kinds of things that I've tried to do. And of course, the very practical point that computers, well, nowadays they're absolutely all around us. For me, I had started using computers around 1972, and by the early 80s, I was kind of used a computer all the time, so to speak. So it was kind of the kind of ambient experience of computers, using them, interacting with them. I built large software systems for doing kind of scientific computation and so on. By that time, that was kind of that sort of ambient technological environment was something that I think is pretty critical for the things that I managed to figure out. Without that, I would have not been looking in that direction, so to speak. Plus, when it came down to it, just doing the obvious experiments, one had to have the computational analog of a telescope. And I had that because computers existed, and I'd written a bunch of software that made that possible and so on. And so that was a thing where, even though I didn't know what the answer would be, it was easy enough for me to do the experiment that I actually bothered to do it, so to speak. And had that not been the case, those are not things that I think I would have been able to discover at that time.
Right. So it sounds almost as if computers themselves were more of an influence than other people in this case.
Yeah, I suppose you could say that. Yes. I mean, it's one of the things that is remarkable about, I spend a lot of time doing computer experiments. It's like, I wonder what happens if you do this. I can just get the computer to do it. There's no, oh, I have to go ask a person what happens. It's just run it on a computer, see what happens. It's when one does experimental science, it's typical experimental science is much, much harder to do. I mean, I spent my life building tools that make this really easy, but and not only for me, but also for lots and lots of other people in the world, one could just walk up to one's computer and use all these tools I built, for example, to just do a computer experiment and learn something, do something nobody's ever done before, and learn something new. And it can happen in a minute. And, if one was doing physical experiments, there's all this, setup of, clean the apparatus and do this and that and the other, which one doesn't have to do in the case of computer experiments. Well, one doesn't have to do now because I spent decades building tools that make it really easy to just walk up to the computer and start doing those experiments.
Okay, so getting back to setting the scene, Stephen. So what you just described, basically that systems beyond a certain relatively low level of complexity, so most systems in the natural world, whether more or less complex, require a level of computation that sort of blocks us from predicting precisely the outcomes of these very, very complex interactions.
Well, I didn't quite get to that, and maybe I should get to that.
Yeah, I was going to say, this is the important discovery of the principle of computational equivalence, right?
Right, and a bunch of things that leads to. So one thing, okay, first point to make is when you look at some system in nature and you say it starts in this way, and then nature just runs and something happens in that system. One thing to realize is you can describe that as being like a computation. When we do a computation, we have some input, we go sort of compute, we get some output. We can kind of think of the processes in nature as computations like that. Question then is, how sophisticated are the computations that are going on in nature? And one way to kind of start answering that is to say, if we use different kinds of rules for these computations, is it the case that when the rules are really, really simple, the computations are somehow very simple, and as the rules get more and more complicated, the computations somehow get correspondingly more complicated? That's what you sort of might think would happen. What actually happens is, above a very low threshold of sort of complexity of rules, it turns out that the sophistication of the computations that get done are all the same. So, and that means, so you might think, oh, I have a computer and I start adding all sorts of different things to its CPU, and I start giving it all sorts of capabilities to do this and that other thing. Oh, if I do that, then I can do fundamentally different kinds of computations than I could do with a simpler computer. That's not true. You can always make, just by changing the program that you feed into the computer, you can always make that computer, even though it may have simpler underlying rules, do things as sophisticated as the computer that has more complicated underlying rules. And that's an idea that one already knew was very important, because it's kind of the idea of that it's related to the idea of universal computation, the idea that you can have sort of a single computer that can run sort of all possible programs that you might expect a computer to be able to run. I mean, back in, around 1900, for example, if you'd ask people, what kind of a thing do you need to do addition? They would say, well, you need a machine that has these cogs and so on, that does addition. Say, what kind of a machine do I need to do multiplication? Oh, you need this other kind of machine with a different set of cogs and so on to do multiplication. The big discovery that kind of got clarified with Alan Turing's work and Turing machines and so on in 1936 was that that's not the case. You can have a single kind of universal computer that's capable of doing all these different kinds of computations, and you can achieve that just by using different software. That's kind of was the thing that eventually launched the kind of computer revolution, launched the idea of software, gave us kind of pretty much today's modern sort of computer technology infrastructure and so on. But that was kind of the idea that it is possible to build a universal computer. The thing that I kind of discovered is that not only is it possible, it's actually something that's really easy to achieve, that as soon as you get above some very low threshold in kind of the rules that you're using to set up the system, you immediately get to this place where you're capable of doing any possible computation. And this leads to this thing I call the principle of computational equivalence, which essentially says that above that very low threshold, all systems tend to be equivalent in the sophistication of computations they can do. So that has an important consequence, not too hard to understand. which is if you're trying to predict how a system will behave, you are, in a sense, competing with it as in terms of the computations it's doing. So the system is running, it's kind of doing a computation to figure out the behavior of the system itself. You, as the kind of predictor of the system, are also doing a computation with your brain, with your computer, whatever else, and you're trying to predict what that system is going to do. So you might have assumed, oh, that's just a little system in nature that has very simple rules. I'm going to be, because I have a much more sophisticated brain, I'm going to be able to just jump ahead. And even though it took it a billion steps to figure out what's going to happen to it after a billion steps, I'm just going to be able to, write down a formula and in one fell swoop, so to speak, just say, here's what's going to happen. But this principle of computational equivalence says that's not the way things work, that in fact, the computational capabilities of my brain or my computer or whatever else are no greater than the computational capabilities of this system with its simple rules. And so what that means is I can't expect to jump ahead like that. I'm forced to basically just follow the whole sort of irreducible computational process that the system itself follows. And that leads to this idea of computational irreducibility, the idea that there are computational processes where you just have to follow each step to see what's going to happen. And that idea of computational irreducibility just has an amazing number of consequences, which it's taken me sort of decades to progressively understand what all these various consequences are, whether they're for how we think about AI ethics, how we think about free will and consciousness and so on, to things about what we can predict in science, to things about sort of how the fundamental physics is put together and so on. This idea of computational irreducibility is really an important idea. And I think it's one of these things that at some level, it changes one's view of kind of how to think about science, because kind of the thing that came from sort of the mathematical science of the 1600s is we're going to get a formula for that. We're just going to say, science has told us this is what's going to happen. We're done. What computational irreducibility shows us is that from within science, science is telling us that's not going to work in many cases. You're not going to be able to just jump ahead and say, we got a formula, we're done. Rather, to know what's going to happen, you actually are forced to sort of follow each step and see what happens. So that's and I think, as I say, that has all these different consequences. It's even, for example, for since you have the words chasing consciousness behind you, I have to make a comment about that.
Please do. I mean, I would love to zoom in on the limits of science question, but feel free to comment on consciousness first.
Well, I think one of the things that is always a question for us as we lead our lives and sort of time progresses and so on is the passage of time meaningful? Because, if there wasn't computational irreducibility, we could expect that we'd just be able to jump ahead and say, what's going to happen to me eventually is I'm going to land on the number 42 or something. And the sort of the passage of time that is the progression of one's life or whatever, nothing would be achieved by that, because one could always just jump ahead and say, this is the answer. Computational irreducibility is the thing that sort of makes the passage of time meaningful. And I think that's...
And it roots us deeply in that passage of time and all of our science. And that's my question regarding the limits of science. Can you comment on, you mentioned how many implications it has, but let's talk about the irreducibility for the limits of science, whose job basically is to predict the behavior of the physical world. So if we can't do that, and if all of our science is also deeply rooted in the notion of time, what does that mean for the limits of science? And how's that changed the way you see the way we should do science?
Well, so one feature of computational irreducibility is that within any computationally irreducible system, there are eventually an infinite number of pockets of reducibility. In other words, to know everything about what will happen is an irreducible question. But there will always be particular things that you can say. And actually, when we come to talk about sort of fundamental physics and so on, one of the things that happens there is sort of the underlying dynamics of the universe is deeply computationally irreducible. But our existence sort of is within certain pockets of reducibility. It is if we just took the sort of the kind of underlying rules of physics and we just looked at those and we didn't we would probably say, how can we predict anything about what's going to happen in the world? Well, what's happening is that we are kind of keying into certain pockets of reducibility. And that's how the world comes to be a place that seems somewhat predictable to us. So a good example of this is you have a gas and it's got a bunch of molecules bouncing around, and the details of how those molecules bounce around is full of computational irreducibility. But when we observe the gas, the main thing that we concentrate on is the very large-scale aggregated motion of those molecules. And turns out that certain features of that are computationally reducible, so we can write down simple formulas for pressure and volume and temperature and so on of gases. And those work because we've kind of keyed into this pocket of computational reducibility, and we've not had our noses rubbed, so to speak, in the computational irreducibility of the detailed motions of all these molecules. So the thing is, there are things in science where we're going to find these pockets of reducibility where we are going to be able to say things, and then there are going to be things where there is irreducibility where we're not going to be able to say things. And sometimes the things that we really care about saying will turn out to be things for which there is computational reducibility, and we can write down a formula and sort of jump ahead. Sometimes the things we really care about will not be things that are computationally reducible, and there really won't be a choice but to just sort of follow each step and see what happens. And the fact that there is that branch where it might be the case that science can't just say we're going to be able to predict what's going to happen is something that I think people are sort of, well, the vast mass of people, I would say, have not yet come to terms with, because people are still kind of in that 1600s type model of what science is, which was very surprising at that time, but 300 years later seems obvious to people that there's just a formula for things, and that's what science is about. The thing is that if science is about kind of knowing how things ultimately work underneath, then it is not the case that just because you know how things work underneath, that you can just sort of work out a formula for what the end result of everything will be. So I think that when people, sort of a general assumption that it has to be the case that science can just give us a formula for everything, and that's just not true. And we should be glad that it's not true, because if it was true, as I say, things like the passage of time, our perception of free will, and so on, all these things just wouldn't work. And so it's sort of there's the kind of if you want your world to be completely predictable, then you can that has the downside that then you can know what's going to happen, and that's kind of that sort of denies the
great mystery of the universe, the great curiosity of being alive.
Yes.
A note here on Gödel's incompleteness theorem. Are you suggesting that these little pockets of which we can predict are sort of floating, not in relation to each other? Because I was reminded as you spoke of the relational interpretation of quantum mechanics, this idea that we can't really say what things are in and of themselves, but we can speak about their relations. Can we form relations between these pockets to create a theory of everything, or is it really just even naive to talk about the possibility of a theory of everything?
Okay, there's two different pieces here. So for example, Gödel's theorem, the sort of a big question there is, if you, in math, for example, you can start from certain simple axioms. For any numbers x and y, x plus y is equal to y plus x, and a bunch of other axioms like that. Those are kind of like simple rules for building math. Now the question is, if you have those simple rules for building math, what can you reach? Are there things that are math questions where, for example, you might need to have an infinite length of proof from those underlying axioms to get to that question. That's kind of the essence of Gödel's theorem, is that from those axioms, there is no guarantee that a proof of any particular statement or the fact that the statement isn't true as well, that's a finite thing. And that Gödel's theorem is actually a kind of a sort of a consequence of computational irreducibility, because computational irreducibility talks about the fact that to know what's going to happen, you kind of have to follow each step. So you say, well, what happens in the end? Is there a proof of any length? I don't care how long it is, just any length. What's going to happen in the end? That's something which in general you can't finitely answer in a computationally irreducible system, because you're stuck going through each step. And if you say, well, it could be an infinite number of steps, well, it might take you an infinite time to find that out. Now, in terms of what is, in a sense, so computational irreducibility is why math is hard. If it was the case, if everything you wanted to work out in math was computationally reducible, there would be nothing, you just always be able to jump ahead and say, okay, that's the answer. You don't have to, math wouldn't be hard. What is not obvious about math, as math has been done by sort of in the history of human mathematics, is that math is actually, that it's doable at all. And in fact, I think that's a very interesting phenomenon. In practicing practical mathematics, these problems of so-called undecidability, this question about are the proofs of finite length and so on, those questions don't occur very often in practical mathematics. And the reason for that is that practical mathematics, like a lot of other things we humans choose to do, lives in certain pockets of reducibility. To give a sense of that, if you're trying to do some math, some kind of fairly elementary math about geometry and trying to prove things, and Pythagoras' theorem and things like this, you could say, well, I can use Pythagoras' theorem to prove this or that thing. But really, the statement of Pythagoras' theorem in terms of the underlying axioms of mathematics is pretty complicated. And you might say every time you try to prove something in terms of Pythagoras' theorem, you really have to go down and see how that works in terms of the low-level axioms. You have to go sort of millions of levels down to look at these low-level axioms, and you won't be able to operate at this kind of high level. So the analogy of that is in something like you're thinking about the flow of water or something like this. You might say it's not good enough to just talk about the velocity of the water and the overall kind of pattern of flow and so on. You've got to go down and look at the individual molecules to find out what's going to happen in the water. And so the fact that mathematics, as done by mathematicians, is possible is sort of the same, for the same reason that it's possible to talk about the flow of water without going down to the level of individual molecules and so on. Mm-hmm. So that's roughly the connection. I mean, it's actually, I think, a very deep connection between sort of the doability of human mathematics and our perception of the physical universe as kind of human observers of what's computationally possible in the universe.
And that's something we're about to get into. But just to finish on this point, taking that idea back to science in general, these pockets, my question was about relation theory, this idea that, okay, we can't say something fixed and universal about the whole world in all contexts, but can these little pockets be related? Can we form a sort of network of little bubbles of reducibility and create a theory of everything from that? Or is that naive?
Well, okay, so there's a different question. What does a theory of everything mean? So, we'll probably talk about a lot of really surprising kind of progress that we've made in recent years in understanding kind of what everything is made of, so to speak. And I think we understand at this point, I'm pretty confident that we understand sort of what the universe is ultimately made of. But those low-level structures and rules and so on for the universe, there is incredible computational irreducibility in going from those things to everything that happens in the universe. But the fact is that our experience of the universe is mostly about particular pockets of reducibility within that vast amount of computational irreducibility. So the thing that I think we can say, and I think we're pretty much there at this point. I mean, many details to fill in, but I think the big conceptual framework is there to say we really do have a theory of how everything fundamentally works. But that doesn't immediately tell us, can we make a starship with warp drive or something like this? There's a sort of irreducible distance between sort of the underlying stuff, that the underlying framework by which the universe is set up, and all the particular questions you might ask about how the universe works. Now, if you ask the question, is it possible to get to all questions that are kind of sort of all reducible questions? Is there are there stepping stones through reducibility to get to every reducible question? I think the answer to that is no. I mean, that relies on, that depends on, it's
why I love the relational interpretation of quantum mechanics, because it comes back to these actually quite ancient ideas that we can only really talk about things in terms of other things rather than in terms of in and of themselves. So
yeah,
so
I think that issue of talking about things in relation to other things, I think in the end, the way that we talk about the universe is deeply kind of, in a sense, egocentric to us. I mean, our perception of the world is about what happens sort of internally in our internal experience, in our minds, so to speak. And there's a sort of tremendous, I mean, to me, very surprising. I would not be the way I would have expected things to come out, but it's the way that they seem to come out, that there's this very surprising relationship between the way we are and the way that we perceive the universe to be, so to speak. So in that sense, it's a that's something that you can't separate us out. If it's kind of the very non-human aliens, so to speak, observing the universe, the physics that they will attribute to the universe will be very different from the physics that we attribute to the universe.
Well, this is something I really want to come on to. So if you don't mind, Stephen, I'm going to bring us on to observer theory, because it's a subject we've covered a lot in relation to quantum mechanics here on the show. It's something you've been thinking about a lot, and you've got a wonderful blog post about it, which you'll find in the show notes, listeners, like everything else we're going to talk about today. So as observers, we are computationally bound by our brain's limited processing power, but we're also bound, as we've been talking about, by this context and perspective, constrained by being in a certain place in a certain time. So perhaps even to introduce the implications of these observer limitations to the way we formulate our scientific laws, or rules, as you call them in computer science, could you introduce the way your work on the Wolfram Physics Project has modeled the possible history of the universe using these various levels of abstraction? So first, the emergence of physical space. Then secondly, the emergence of branchial space, so modeling these possible quantum histories. And thirdly, and lastly, the Rulial Space, this third level of abstraction with multiple possible alternative laws or computational rules that could govern a universe completely differently, should it be seen from a different observer's point of view. Maybe introduce those three levels of abstraction to introduce observer theory.
Right. So we're descending through layers of the deeper and deeper into the rabbit hole, so to speak. But let's start off with kind of our physics project. So, one thing to say is 100 years ago, there was a rapid advance in physics. In discovery of general relativity, relativity theory, quantum mechanics, and so on. A lot happened 100 years ago. We've been kind of living off those advances in physics for the last 100 years, mostly in physics. It's been really exciting that the last 3 or 4 years, it seems like we have another burst of kind of realization of there's really new ways to think about physics. In a sense, they go back to much longer ago, because back in antiquity, people were arguing, is the world made of discrete atoms, or is it continuous? Is it like something like the perception of a fluid like water or something, or is it made of ultimately of discrete elements? People argued about that in antiquity. People continued arguing about that for 2,000 years. And finally, in around the beginning of the 20th century, it got nailed down. Matter is discrete. It's made of atoms, molecules, etc. That's done. Similarly, light turned out, one could think about light as discrete, made of photons and so on too. Back 100 years ago, a lot of people thought, well, space is going to turn out to be discrete as well. But nobody could quite figure out how to make the math of that really work. So that kind of fell by the wayside, and people concluded, well, okay, these other things are discrete, but space is continuous. That means you can just describe it sort of in the way that Euclid described space, as just this thing where you can put something at any position in space, described by a number. Well, the sort of starting point of our physics project is the realization that actually it is true. Space is not continuous. Space is discrete. What's space made of? Space is made of just discrete points, discrete elements, and there's nothing that one can say about these elements other than that they are distinct from each other and that they are related to each other. A given element can be related to other elements. It's kind of like a given element can be friends with a bunch of other elements. And so what you build up is this kind of graph, this network of sort of which element, underlying element is related to which other underlying element. You build this big network. And the idea is this big network is the universe, basically. There's nothing in the universe other than this network which makes up space and everything in space. So how do you make something like a particle or a black hole or something like that? It's just a feature of the way these relations, these connections between different elements are set up. So, for example, if you were thinking about, I don't know, think about water again, and you've got all these molecules in water, but you can have an eddy in the water. That's this sort of thing that you can see kind of spinning around in the water, just made of water. But the point is that that eddy has a certain sort of existence independent of the fact that it's made of these underlying molecules. And so similarly, we think that things like particles, like electrons and so on, have that same kind of emergent existence in this network that represents the universe that something like an eddy has in the case of water made of molecules. We know this pretty explicitly for black holes. We have pretty good modeling, detailed modeling, where we can compare it with experiments that of observations that people have made of black holes and mergers of black holes and things like that. We can see pretty clearly how that works in this discrete model of space. One thing I should say is that kind of the state of the universe is a particular configuration of this network. You can ask, well, what's time? Well, time is the sort of computations that are going on to update this network. So the idea is there are some rules that say, hey, if you have a little piece of network that looks like this, then the rule will say to update it to a piece of network that looks like that. And those rules are getting applied all over the place throughout the universe, throughout this network. This network is being progressively updated. And so the progress of time is that sort of progression of computation that is updating this network. And one thing that's sort of an interesting historical point is back in the beginning of the 20th century, kind of relativity theory was very elegantly described mathematically by saying space and time are really the same kind of thing. But actually, in our model, space and time are very different kinds of things. Space is the extension of this big network. Time is the progression of computation applied to this network. And it just turns out that when you work out the math and so on, that it emerges that, well, there's a tricky point about the fact that to an observer embedded within that setup, it necessarily is the case that space and time will appear similar in just the way that relativity says that they appear similar. But that's not something that's intrinsically built into the model. So it's a bit confusing because, in the elegant mathematics of 20th century physics, it's very convenient to just sort of package space and time together, but that's actually a misleading thing to do. But so actually we can understand that this network, it's getting updated, all these little pieces are being sort of rearranged, and we can ask the question, well, what's the large scale effect of all that little rearrangement and so on? It's a little bit similar to asking, in the case of molecules bouncing around in a fluid, what's the large scale effect of that? Well, the large scale effect of that is all the laws of fluid mechanics and so on. The large scale effect of all these little pieces of network being rearranged turns out to be the known overall theory of space-time, general relativity. And so you can work out things like, what is gravity? You can figure out how gravity works and how gravity has to work in a system like this, consisting of this network that's progressively being rewritten. So anyway, that's kind of the first big thing is
physical space.
We make space, right? Space is being made. I mean, in the end, it's perhaps a little disappointing because all the stuff that we care about that happens in the universe, all those photons and electrons and protons, all those kinds of things, those are a tiny bit of fluff on top of the main activity of the universe. The main activity of the universe is knitting together the structure of space. Most of the updates that happen in this network, probably only 1 part in 10 to the 100 or something or less of the activity that happens in the universe is devoted to things that will to us seem significant, like there's a photon of light traveling from here to there. The vast majority of what's happening in the universe is merely the processes that knit together the structure of space. And it feels a little bit disappointing in a sense that things we care about are just this little tiny, tiny fluff on top of the vast majority of the activity, which just has to do with sort of maintaining the infrastructure of the universe.
And how does that then have the next level of abstraction when we start talking about branchial space?
Right. So what I've talked about so far is there's this network, actually technically a hypergraph, and this thing is being rewritten, and there are these rules that say, okay, turn this network that exists now into this next network that exists at a moment later, and so on. Well, okay, there's a tricky thing here, which is the rules just say, if there's a piece of network that looks like this, it gets rewritten into one that looks like this. But there are actually many different ways to apply these rules. So if there's just one way to apply the rules, there'd be just one sort of path of history for the universe. But actually, there are many different ways to apply these rules. So you end up with many paths of history for the universe, many different possibilities for what can happen in the universe. And so you have this kind of whole structure, we call it a multi-way graph, of sort of branching and merging of possible states of the universe. Actually, this multi-way graph, these kinds of things show up all over the place if you start looking for them. Let's say you're playing a game of tic-tac-toe, noughts and crosses, depending on where you're from. You put down a particular configuration of the board, and then there are two different choices you might make about where you make the next move. That produces a branch, these two different states of the tic-tac-toe universe, so to speak. And you can, often it branches, but sometimes two different sequences of moves will end up with the same configuration of the board, and that's a merge. And so that's an example, a very small multi-way graph. The one that makes our universe is an awful lot bigger than that. But what happens is there's this sort of branching and merging of possible histories for the universe. So when you look at a particular time, you'll find that there are many, many, many different branches of possible histories of the universe. One thing that's significant is those branches are related to each other. Because, for example, two branches might be the result of something that's split just one step before. And so you can kind of make this map of how all these different branches are related to each other. And that map of how those branches are related is not the same, but it's the same kind of idea as the way that we understand how different elements of space are related to each other. But this is not ordinary space. This is what we call branchial space, the space of possible quantum branches, as it will turn out. Well, all these different possible histories for the universe, they're what make quantum mechanics. And the thing that is sort of, when we observe physical space, physical space seems continuous to us because we're very big compared to these individual atoms, these individual elements of space. And so we are sort of averaging over huge regions in terms of the atoms of space. Same thing happens with matter. We think matter is continuous because we're not seeing the individual atoms. We're just seeing this aggregate of very large numbers of atoms. So so in the case of physical space, we perceive space to be continuous because we're very big compared to the atoms of space. Now, something a little bit more difficult to understand is in the case of branchial space, our minds are also extended in branchial space. We exist across many possible branches of history in the universe. And so, in a sense, what we have to think about, what we have to think about in quantum mechanics is how does this mind that consists of many different branches perceive a universe that consists of many different branches? And that interplay gives us quantum mechanics. And it seems to be very beautiful. I mean, there's a lot of I dotting and T crossing still to be done on the mathematics of all of this. But what seems to emerge is that, well, in quantum mechanics, the sort of defining mathematics is this thing called the Feynman path integral, which is kind of a formula that tells you gives you quantum amplitudes for different kinds of for different processes and so on. And when it turns out that, in a sense, what leads to gravity in physical space, gravity is the idea that kind of paths of things are deflected by the presence of energy, momentum, mass. That's the essential idea of gravity, and we see that emerge in our models of physical space. The corresponding thing in branchial space is a sort of form of gravity in branchial space, which turns out to give us exactly the path integral of quantum mechanics, or seems to. And so, in other words, what is in physical space is gravity. In branchial space is the core idea of quantum mechanics. So that's a pretty cool thing that, people have kind of wondered what's the relationship between general relativity, theory of gravity, quantum mechanics, and so on. The answer is they're actually the same theory in some sense, just played out in different kinds of space, so to speak.
A quick aside, Stephen. How does this branchial model relate to the many worlds approach? Is it the same as? Is it compatible?
It's a little different because the first thing is in the many worlds version of things, it's kind of like a consciousness exists in a single thread and those threads don't merge. It's very important in our setup that these threads are branching and merging, and that our experience of the universe spans many threads of history. And the fact that that's consistent, the fact that we can say, yes, we aggregate these many threads of history, that possibility of that being consistent relies on this fact that there can be merging as well as branching. So there's a kind of the sort of the beginning of kind of the many worlds idea that there are many paths of history, which is also built into the mathematics of the path integral. That's kind of the same beginning, but it goes to a different place. In fact, well, there's lots of nice kind of mathematical connections, but from a conceptual point of view, this is sort of taking it in a bit in a further distance, so to speak.
And then taking it one level of abstraction even further, that within these various branchial spaces, these various possible quantum histories of the universe, there is Rulial Space, which is this vast, seemingly infinite possible rules, different rules that could be applied computationally to each one of those branches.
Exactly.
And you call this Rulial Space.
Right. So here's the thing. I found this very confusing for quite a while. The thing was, we're saying, okay, let's find a rule that says how this network is updated, how all these branches get produced, and so on. I just sort of was imagining the moment where we can say, we've figured it out, we've sort of reverse engineered the universe, here's the rule. Let's give you this rule. That's very confusing because the next question is why that rule and not another rule? why did we get universe number 3812 or something? And now the thing, so what we then realized is that actually, here's the way to think about it. You just think about, just like a given rule is being applied in all possible ways, you can say, well, why don't we just apply all possible rules? And you might say, that's just going to be a total mess. What are we going to be able to conclude by applying all possible rules? Well, the answer is, it's a little bit sort of brain twisting to think about, but you have this thing that represents sort of the application of all possible rules in all possible ways. We call this thing the Ruliad. It's kind of, you can think about it as apply all possible computational processes to all possible initial conditions for an infinite time. So it's this complicated, entangled mess of possibilities. It has a lot of structure, partly because when there are things that, when there are sort of two distinct, two sort of branches that emerge, those branches can merge again, and that kind of generates a structure for what's inside this Ruliad. The Ruliad is not just a collection of independent sort of threads of progression. It's this very sort of complicated, entangled thing. And so then the question is, well, what does an entity embedded within this Ruliad, made of the same stuff the Ruliad is made of, how does that entity perceive what's happening in the Ruliad? And the thing, so this concept of Rulial Space is this idea that just as when you pick a different place in physical space, you have sort of a different point of view about the universe, a different place in Rulial Space corresponds to attributing a different rule to the behavior of the universe. And what's this idea of principle of computational equivalence and so on tells one that actually these two different rules that you might attribute to the behavior of the universe are in some sense equivalent. You can find a translation between them. So that means that there is that's kind of why one can make general conclusions, even though there are different particular places one can be in the Ruliad. It's just like we can say general things about physics, even though, we go from, we believe that physics is sort of the same if we were living in a different galaxy and things like this. So kind of the idea is, in the end, that if you think about sort of different observers of the Ruliad, kind of different minds observing the Ruliad, they exist at different places in Rulial space. We can kind of travel between them. We can make translations between them. And, we can see this at many levels. I mean, even at the level of thinking about different human minds, we all have different detailed sort of patterns of neuron activity, so to speak, different electrical signals going on in our brains. Yet, and that means that our brains are sort of exist at different places in Rulial space, but we get to make some translation from the nerve impulses in my brain to the nerve impulses in your brain. Somehow there's something, it's some kind of, in the case of Rulial space, it's more like sort of the concepts that get represented in one brain can be transferred to another brain. And that's
this is exactly what I wanted to ask about, Stephen. So I'm just going to plug a little question in here. So we've got this, we're very familiar with this kind of sea of more or less probable laws and rules. We're quite familiar with these ideas for anyone who's been thinking about quantum mechanics. And the conceptual representation of all these different possible configurations of rules in the universe, for me, the implication of your observer theory, when you plug it into the Ruliad, is that our species' particular computational approach, the sum of all of our best theories of science that have been born out of it, deeply bound to this unique context and this observer's perspective. And what interests me from the point of view of another intelligence navigating in some quite different branch of the Ruliad, whether biological or artificial, by the way, so it could also be an artificial intelligence, doesn't have to be biological, would have a completely different window into the world, as it seems, and therefore, using your word here, pass a quite different scientific laws and concepts from its observer perspective.
Yeah.
For me, that's the implication of the Ruliad when plugged into observer theory. Have I got that more or less right?
Yes. I mean, look, the first thing to say is that you don't have to make many assumptions about observers like us to get precisely the laws of physics that we now believe are operating. And that's a very non-trivial fact, because it could be the case that you would have to start saying, oh, we have two eyes and we do this and that and the other, that we need all of that to conclude something about laws of physics. But we don't. We only need the fact that we are computationally bounded and that we believe we are persistent in time, which is a non-trivial assumption, because at every moment we are made of different atoms of space. So the fact that we have this continuous thread of experience is a non-trivial assumption that we're making. In some sense, looked at from the outside, it's like, what do you mean it's the same you at the next moment? You're made of completely different atoms of space. How can you say it's the same you? But we have this internal perception that it is the same us. And that internal perception that it's the same us drives many things. For example, in quantum mechanics, it drives the fact that we believe that definite things happen. There are all these threads of history, and they're all doing potentially different things, but somehow we conflate them all together and say, we insist that there's a single thread of history. And the fact that it's consistent to do that, and the little inconsistencies that happen temporarily, those are sort of the essence of what we actually observe in quantum mechanics. But it's the idea that, so there are these very coarse assumptions about observers like us that are sufficient to give us, not just in vague terms, but in precise mathematical terms, the particular laws of physics that we've discovered in the 20th century. But so now the question is, well, what about observers not like us? It's quite difficult.
This is the big question. Is there a computational language that could eventually bridge that gap and become a multi-computational language? I know that your long-term vision has been to create a computational language that could symbolize all possible ideas, all images, all functions, all rules. Can Wolfram Language, that you began developing in 1988, listeners, a long time ago, could it eventually bridge such a gap? Or is it impossible to know because we just can't imagine how differently such an entity would conceptualize its universe?
Wolfram Language is for humans. And what it really is it's a bridge between the way we humans think about things and what's computationally possible.
Right.
It's taking that slice of the Ruliad, effectively, that is sort of accessible to observers like us, and it's trying to represent as much of the world as possible in computational terms, in precise, sort of formalized computational terms, and that's a very powerful thing to do. I mean, just to sort of mention that for a second. I mean, the whole story of kind of human thought is a story of how we formalize things. I mean, back before we had even human language, I'm sure people were like just pointing at things and saying, that thing, the tree. And then they realized, we're pointing at these things. They're all the same kind of thing. Let's call it a tree. We have this word in human language. We've sort of formalized the concept of a tree. And then came logic, and then came mathematics. And now we have computation as a way to kind of formalize our description of the world. And it's really powerful to be able to formalize things, because it lets you go beyond kind of the mere, I'm going to think about this and then this. It lets us automate thinking about things. This has been the story of what I've kind of tried to contribute to the world from a technological point of view, of providing this kind of computational language to describe things in the world, so that you can kind of build these kind of big automated formal towers to talk about those kinds of things. But our market is humans, and so what we're doing is trying to make something which is a convenient representation of computation for human minds. Now, if you say, well, what would the dolphin version of the language be like? We don't know, actually. It's an interesting question. But the primitives that are there of describing things in terms of, objects and so on, and solid objects and this and that and the other thing, together with all the cultural stuff, which is very specific to humans about, the geography and countries and things like this. I think probably our description of, for the dolphins, it will be very different. We don't know exactly what it would be, but dolphins are really close to us in Rulial Space. I mean, we're, the kinds of, human minds of sort of different educational, cultural backgrounds and so on, they're sort of progressively further away in Rulial Space. By the time we get to your average, somewhat understandable mammal, it's further away.
You just got me started on a sort of thought experiment of imagining another entity on a different branch, potentially in a completely different Rulial space with a whole bunch of its own laws of physics. Obviously there's a lot of speaking now about extraterrestrials now with all of this obsession with space, even potentially extra-dimensional entities or intelligences. I think it's a really interesting thought experiment. And it got me thinking, if one of these entities could somehow pick up Wolfram language on some kind of signal, could they interpret it? Could they get the image you're representing?
Right, good question. I mean, it's a, okay, there are multiple pieces to this. So I think the first thing to say is about sort of intelligence in the universe. And this principle of computational equivalence kind of says there's intelligence all over the place. The fact that our brains do these things that are very computationally sophisticated and so on, and we're very proud of that. It's like, that kind of stuff is happening all over the universe. I mean, there's this common saying, the weather has a mind of its own. What does that mean? It means the weather does things we don't expect all the time. Well, why is it doing that? It's doing that because there's computational irreducibility in the weather. And all the dynamics of, all these little air currents and so on that are happening, and formation of clouds, all this kind of thing, that's kind of like the kind of computational processes that are going on in our brains. Not in detail like them, but at a computational level, it's the same sort of level of sophistication. So, if we think about the sort of Rulial space of where are these different things, okay, we can more or less understand what's the cat thinking. It's much harder for us to understand what the weather is thinking, even though I think that the weather can be thought of as an intelligence in some sense like us. So when we think about, extraterrestrial intelligence, your average pulsar with a complicated magnetosphere and so on, that's producing radio signals that have very complicated structure, that is, in some sense, an intelligence. It just is a very non-human-like intelligence. And this question about how do you bridge between sort of human-like intelligence and this kind of intelligence in the universe, in a sense, the role of science. That's the role of natural science. Natural science is about taking kind of what actually happens in the world and trying to produce kind of a human narrative about what's going on, trying to make understandable to humans what is out there in the natural world just happening, so to speak. So in a sense, what you're asking for is, you say, I want extraterrestrial communication, so to speak. It's like, I want to understand what that pulsar is saying. Well, in a sense, that's translating what's going on in the pulsar into a human narrative. Now, we will just say, oh, it's just natural science, but you could as well say, it's sort of a conversation that's going on between the system in nature and the things that are going on in our brains.
Well, it's just as probable that there's extraterrestrial life out there, biological life, as it is that there's artificial intelligence out there, which is going to be the subject of the second part of our conversation in a moment, listeners. But again, even if that artificial intelligence is on a different branch or has a completely different Rulial conception of the universe, could it be interpreted via Wolfram language, for example?
Well, okay, so here's a much more near-term thought experiment, okay? We humans believe in space. We think about, there's space, there's time. Well, one reason we think that there is a notion of space is because of our everyday experience. We look around, I'm looking around this room, I can see, 10 meters away from me, okay? Light is coming to me from something 10 meters away. It takes a microsecond to get to my eye. My brain takes milliseconds to respond to what it sees. So as I look around, it seems to me that there is a state of things that are around me that are coming to me within microseconds, and I'm not noticing what's happening until thousands of times more time has gone by. So for me, it's as if there is an instantaneous state of space, and I can perceive it, and that progresses through time. Now imagine you replace my brain with digital electronics that runs 1,000,000 times faster. Digital electronics would not, the light that's coming to me, it's no longer the case that I can say, oh, I can gulp in this whole scene of this whole area of space before I've had the next thought, so to speak. I'm going to have the next thought before the photons have arrived that come from this object that's that distance away. So my kind of conception of space will be different. I mean, it would be, for example, let's imagine you're just a little computer that's sitting on the internet, and all you know is the connectivity of the internet, so to speak. Do you know what space is? Do you conceptualize the idea of physical space? Because what you know is the internet connections, which are, maybe you notice there's timing features of the internet connections where you say, oh, there must be a two-dimensional surface of the Earth, because I can see that the time it takes for this signal to travel this place, and so on and so on and so on. It won't be an intuitive thing that there is a notion of space. And for example, you mentioned, dimensionality. Well, in our models, one of the things that happens with these networks is space is not necessarily precisely three-dimensional. It's in these networks, there can be dimension fluctuations. In fact, the beginning of the universe was probably infinite dimensional, and it gradually kind of cools down so that things are only as connected as you get in 3 dimensions. And there are probably little dimension fluctuations left over. We're kind of hoping that those might actually be observable in astrophysics experiments and so on. That will be exciting. It will be kind of a pretty in-your-face indication that this whole idea of discrete space and so on has to be that way. But I think this question of why do we parse the universe as a three-dimensional thing is probably a consequence of the fact that we're observers of the kind we are. It's probably the case that different observers would say, what do you mean? You've aggregated the space together and you put it all together in 3 dimensions. I just believe in, following this sort of space-filling curve path that visits everything sort of one atom of space at a time, so to speak. So it's kind of a, I think this point about kind of other intelligences, alien intelligences, sort of how do alien intelligences view the world? It's there's a lot more intelligence out there than one might imagine, and really the question is just, can we translate from human intelligence to that? And I think it's it turns out, well, there are interesting features of biological life that sort of, at least to us as observers, seem very special relative to what else is happening in the universe. I don't know to what extent that's really correct, or to what extent that's merely a sort of an effect of observers like us that are built from the technology stack, in effect, of biological life, perceive that the features of biological life are very special, so to speak. It's something that still trying to untangle that. In fact, one of the things that's exciting about the things we've figured out about physics is the kind of formalism. You mentioned multi-computation, this kind of idea of these different branches of history and the way that observers aggregate these branches of history and so on. Those ideas seem to be applicable to a lot of other areas of science, including, for example, things like molecular biology. And they kind of give one new raw material for kind of thinking about how to model those kinds of areas. And I'm sort of hopeful that we'll actually be able to have a better conceptual understanding of those areas as a result of using those ideas. And partly because one's using the same ideas that one's using for physics, the fact that lots of progress has been made in physics, one can import that progress into an area like molecular biology to try and start having real theories of that, where there haven't really been global theories. I mean, if you look at biology, there's not a big theory. It's just biology is the way it is. And we sort of say, well, it's all natural selection and evolution, and it just happens to be that way. But I think there are probably some bigger theories.
And we're all about the multidisciplinary conversations here on Chasing Consciousness. And I just really think that just certainly my forays into biology recently on the show have really shown that there's an awful lot of room for a conversation here. Now, Stephen, I'm going to move us on because I've got one last question before we get to AI, and it's so important that we talk about AI. How it comes up so often on the show, how does your principle of computational equivalence, the consequence computational irreducibility, together with Godel's theorem that we talked about, how does all of that map into the measurement problem in quantum mechanics? Is irreducibility compatible with the sort of collapse of the wave function idea that determined reality only emerges after a measurement or an observation? How do those two ideas relate?
Well, okay, so we don't know all the details of this, but we know quite a bit. And sort of the key question is sort of why do definite things happen in the world? And, in sort of at the raw level of quantum mechanics, looked at kind of from outside the universe, it's like, oh, there are these many different threads of history that are happening. When one does the mathematical formalism of quantum mechanics or quantum computing for that matter, one's always talking about all those threads of history. But the traditional formalism of quantum mechanics from 100 years ago just says, oh, and then you take all those threads of history and you apply this measurement operator and one definite thing comes out. It doesn't say how that happens. It just says that's going to happen. And it's very confusing because there are lots of sort of paradoxical things that come out by just saying, and that's what's going to happen. One thing that our models give one is a way to kind of sort of take that apart and say, well, what is actually going on when the observer is aggregating these different threads of history? But the thing to understand is that's not something where you say there is it really depends on how the observer is doing that aggregation. I mean, the main picture of measurement in our models is it is this process of taking kind of all these threads of history and asking, how does the observer, who is spanning many threads of history, how does the observer aggregate those threads of history? Now, another thing that's confusing is the following. A lot of measurements what is the process of observing things, perceiving things, measuring things? What's actually going on? What's going on is all kinds of complicated things are happening in the world, but when we want to perceive something, what we're trying to do is to take all that complexity in the world and kind of squash it down into something where we can fit it in a finite mind. So, for example, let's say we're measuring pressure in a gas. A bunch of little molecules are bouncing around. They might hit the walls of the container. They might hit a piston. There are all kinds of different ways these molecules might hit the piston. But all we care about is what the overall momentum transferred to the piston is. What we equivalence together all of those detailed motions, and we just say all we care about is this one aggregated thing. That's the essence of what we're doing when we make an observation. It's when we do. So this notion of equivalencing many different states of the world to just conclude this one thing that we conclude. Now, one of the things that's a little bit confusing is that in quantum mechanics, one is typically dealing with, what one's dealing with making measurements where it's like a weighing balance, where you put a lot of different weights on one side and eventually clunk, the balance goes one way or it goes the other way. And one of the things that's a little difficult to understand when you start off from sort of the underlying raw material, the little microscopic pieces, and you sort of aggregate them up. When you're doing fluid mechanics, thinking about pressure and gases, things like this, it's pretty clear that you can think about aggregation of pressure and things like this. If you were dealing with physical materials, you'd also think about rigid bodies, where instead of saying, oh, there's this gas and it's got some pressure, you say, I've got this actual sort of piece of metal and it's going to flip this way or that way. And it's a bit more complicated to talk about that because you have to talk about forces between atoms, the fact that it's maintaining this rigidity as it moves, all those kinds of things. Quantum mechanics is the same kind of approximation, same kind of idealization to sort of all these microscopic processes that rigid body mechanics is to molecular dynamics. So you have to get to ordinary quantum mechanics with qubits and standard measurement kinds of discussions. You have to take this limit that is like, how do you make rigid bodies out of collections of molecules? And that creates a bunch of kind of confusing mathematical complexity in what one's talking about. The flip side of that is that the traditional formalism of quantum mechanics has never successfully set up measurement for quantum field theory, for the analog of sort of fluid mechanics for quantum mechanics. Quantum field theory is what one uses to do all the sort of precise calculations about QED, QCD, all these kinds of things. But measurement is not understood.
Do you feel that the Wolfram Physics project has a sort of answer to the measurement problem? Does it have some, I don't know, something to just make us sleep better? Because it doesn't feel to me like anybody's really, even with the proof of non-local realism, I just don't feel that we're any closer to understanding it.
Right. So I think the answer is yes, but I think that there's more work to be done in some mathematical I-dotting and T-crossing, and some kind of sort of conceptual comfort, so to speak. I mean, I feel like I'm getting more conceptually comfortable with how quantum mechanics works, and the realization that the branchial space is not physical space. For example, a common question, you've got a double slit experiment, you've got, these two different ways the photon can go, and then you have destructive interference, where there are two ways it can go, but somehow what you see is no photon arrives, even though there were two ways it could go. And how could that possibly happen? Well, what you realize is, it looks like in our models, what's happening is that, yes, the photon goes in those two ways, but the photon ends up, it can go through one slit, it can go through the other slit. It ends up in different places in branchial space, depending on which slit it goes through. And the question of, well, what happened in the end is a question for an observer, kind of knitting together these different paths of history, where the photon went through one slit or went through the other slit. And destructive interference seems to be what happens when the photons wind up at different ends of branchial space. And you say, well, why does that make destructive interference? It's because for an observer is a bounded size in branchial space. So if the photon ended up at two completely different ends of branchial space, the observer is really, really trying to get a definite, to say something definite happened in the world, but there's no way they can take those two photons at opposite ends of branchial space and sort of aggregate them together. And that's why the observer just says, oh, the photon disappeared, so to speak. That's a qualitative picture. I mean, it's one thing that's really, really cool, I think, in our physics project, is that there are a lot of kind of ideas in physics where in the past it's just been, there's math, you can work it out, here's how it works. But we're getting to the point where one is beginning to be able to have kind of sort of clear sort of conceptual intuition about why things work the way they work. Like another example, just to mention it, is in relativity, one of the big effects is time dilation. When something is moving faster, time seems to run slower for it. Well, in our models, a thing that's moving, by the way, it's not, the fact that things can move without changing is a non-trivial fact that you kind of have to prove in our models. It's not obvious that that could be true. But let's say you have a thing is progressing through time. It's, this pieces of network are getting rewritten. The thing is just sort of computing its next state and so on. So it does that at a certain rate. Now let's say you're having the thing move. Well, as it moves, it's got to essentially recreate itself at a different place in space. And that process takes some computational effort. And so essentially what's happening is, if the thing is moving, it's using some of its sort of computation budget to recreate itself at different places in space. So it has less computation budget to actually change its intrinsic character. In effect, time slows down for it because it can't use as much of its computation to progress through time. So it's
very, very convenient. It slots in beautifully. And I'm sorry, Stephen, while we're on this physics project, Tell us about entanglement as well, because this is the other one that keeps coming up. How can branchial space help us understand in a slightly different way entanglement without just considering that essentially the particles are the same one?
Well, the entanglement is very directly a story of these threads of history. And when you end up with these sort of two things that are at different places in branchial space, they are entangled quite literally by the fact that their threads of history are connected. They come from a common ancestor in this multi-way graph. Now, the consequences of that as you start looking, so that means that there are correlations between things which are at different places in branchial space. How that will relate to what's measured and where things are in physical space, that's a separate question. But the concept that there can be different outcomes for the universe which are entangled, related in this way, that's something that's very, very deeply built into this kind of setup. I mean, you can start asking, one of the things that happens, okay, so in physical space, the speed of light tells you the maximum rate at which information can be transmitted. And for us, the speed of light, imagine that you make a change in this network. Well, how does the change in the network affect other parts of the network? Well, that change causes the rewrites that are happening right around that change to be different. And there's kind of this cone of changes and rewriting that kind of propagate outward. And if you look at if you say, well, in a sense, the definition of the rate at which that cone expands is the speed of light. And so a change has this progressively larger effect on this network, and that represents sort of propagation of information in physical space. In branchial space, the same kind of thing happens. And so one of the things that is a prediction of our models is that there's a concept of a maximum entanglement speed. There's a maximum rate at which different quantum states can become entangled. There's a maximum rate at which information can propagate through branchial space. And I keep wondering whether there's an experiment one can do to see that.
Oh, it'd be wonderful, wouldn't it, if we could find the right experiment?
We have one thing to do with mergers of black holes where there is probably an effect. It has to do with when two black holes are going to merge. And what's really nice is in our models, we can explicitly simulate that. You can see black hole mergers. Black holes are very convenient because a very tiny black hole works the same as a very big black hole. So even if you're down at the level of atoms of space, you have a black hole, you've got a system with 1 million atoms of space, tiny number of atoms of space, and you have a little black hole there, you have another little black hole, you can see these black holes merge, and the features of the gravitational radiation that come out are the same as the features of the gravitational radiation that come out from giant black holes, the size of the central black hole of a galaxy or something. It's the same. It happens to be something where one can look at it at this very microscopic scale and see sort of the same physics going on.
Now, right. Stephen, I have a suggestion, because the important conversation that I have written down to have about AI safety, about AI solutions is quite long. And I would like to invite you, if we could, to do that as a separate episode. I've really, really enjoyed taking our time over these important principles and getting a good introduction. So I would like to invite you to come back, if we may, and have that conversation on another occasion with that full backdrop of an introduction to all of your theories, and then we plug that into the AI debate, which I know you're fully involved in and have got some great solution ideas as well. And I want to discuss some of the other solutions that will permit us to allow AI to be used to its maximum benefit without it, having any risks to us. How does that sound?
I wouldn't say that. Yeah.
Well, there's never no risk.
It's a good practical suggestion, but I will just say that just to connect these together a little bit, I'm an optimist too. I've spent my life doing very large projects. You don't get to do that unless you're an optimist.
Big time.
Just to connect one thing, this idea of computational irreducibility, that's the thing about computational irreducibility is it means there can always be surprises. And
I've got a really important question about that, but it's just going to take us too long because there's just so many.
Let's make this one connection here, and then we should, another time, let's start by talking about AI.
Exactly. I'd really appreciate it. I'm sorry to ask for you to have to come back, Stephen, but it's such a juicy and important one. And there's so many questions that are actually closely related to the way we've been talking about reducibility and the unpredictability of this particular situation that really means we just have to be very, very humble here. So go ahead, right. Make your point, and I've got one last question about reductionism.
Right. So, I mean, I think one of the things that is going to be, is kind of consider this a teaser for what we might talk about with respect to AI. Sort of a critical societal decision is, on the one hand, we can say, we want everything to be predictable. We want computational reducibility. If we do that, we're constraining our computers to not do what computers can do. On the other hand, we can say, let's let our computers have the sort of full power of what they can do, in which case we have computational irreducibility, in which case we have unpredictable things that will happen. So it's kind of it's a big sort of decision of let's sort of regulate everything, so to speak, and force, if we could do it, it may not be practical, but force everything to be predictable. But then we don't get the advantage that we get from the power of computation, so to speak. Or we have to live with computational irreducibility, just as we live with that in the natural world. Crazy things can happen in the natural world that we didn't expect. And we somehow have managed to live with that so far. But that's kind of a big choice. And that's I think, a key kind of in some sense, deep scientific, philosophical kind of thing to think about sort of the future of AI.
And I would absolutely love to have just a little bit more time to allow you to sort of unfold both your ethical and your practical point of view on that, because I think with all of your experience, how long you've been using automated AI in your company, I think we could just get a lot out of it. So we're going to come back to that, listeners.
Another time.
There's last two questions that are really, really important in the context of what we've been talking about. The first one is about your new book, The Second Law, Resolving the Mystery of the Second Law of Thermodynamics. I'm sorry it's taken us so long to get there, but it was so important to lay this out, and you've done a beautiful job of making it bite-sized for the listeners. I really, really appreciate it, Stephen. Now, you've been obsessing over this question, as you said, since you're a 12-year-old boy. Why is entropy such a mystery? And how has your change in perspective over the years given you insight into it? And, it sounds like it's only recently that it's really made sense to you.
Right. So, I mean, the question is sort of, why do eggs get scrambled but not spontaneously unscramble themselves? Why are there things that, why do things in the world seem to get more random rather than less random? Why is it that when you kind of rub something, you get heat, you get all those molecules that were sort of arranged just going in the direction that you pushed them, so to speak, but they end up as heat where the molecules are randomly running around? What leads to that kind of progressive randomization in the world? And one reason it's really confusing is because when you look down at the level of individual molecules, the laws of physics are precisely reversible. So if you had a movie of just individual molecules bouncing off each other and so on, and you just were looking at, you had 10 molecules there or something like that, or you're just looking at a few collisions, you would look at this movie and you wouldn't know whether the movie was being run forwards or backwards, because all of those microscopic mechanics are completely reversible. So the thing that's been a mystery for a long time is, how does it come to be the case that on a large scale, things look irreversible, even though at a microscopic scale, everything is precisely reversible? That's kind of a version of the question. And the answer ends up being a story of computational irreducibility. And the reason is this, that you're kind of starting things that you say, okay, I'm going to set my system up in some particular state that is very simple and I understand it completely. Okay, but then the system actually runs and it ends up doing an irreducible amount of computation. And then the question is, well, can you figure out the thing that it did with that irreducible computation? Can you how easy is it for you to trace that? How easy is it for you to invert that? And the answer is, because it's an irreducible amount of computation, as a computationally bounded observer, you just have to say, I can't reverse that. It looks random to me. Kind of like what's happening is, it's kind of like encryption. You start off with some key, and you might start off with some piece of text, and you say, well, I'm going to encrypt it, and you're kind of grinding it up computationally to get this thing that looks for all practical purposes random. Now, you can invert it. Otherwise, it would be, it would not be a very useful piece of cryptography if you couldn't ever get the message back. You can invert it, but it takes computational effort to do that. And the point is, what's happening in the second law is that these processes in nature, because of principle of computational equivalence, it is generically true that they do irreducible computation. And the result of that is that we, with our kind of limited computational ability as observers, just can't invert the computation that's happening. And so our perception of that is, oh, it gets more random over time. Now, it's worth realizing that at some level, if you looked really microscopically, the information is still there. So, for example, one thing back in the 1870s, when people first really clarified what they meant by the second law of thermodynamics, people very quickly said there's going to be a heat death to the universe. Eventually, the universe is just going to run down. It's, all these things that right now seem very meaningful, and they're sort of large-scale motions of things. Eventually, it's just going to turn into friction, and it's just going to turn into heat. And the universe is just going to consist of a bunch of molecules bouncing randomly around. That's bad news, so to speak. Well, that picture really isn't right, because what's happening is, it's only to an observer like us that the universe, with all those just individual molecules bouncing around, looks boring. To us, with our computational abilities, we just have to throw up our hands and say it looks random to us. But if we were able to trace things computationally, we would realize that future universe, with all those molecules bouncing around, those molecules contain the information of our whole civilization and, all of that history, so to speak. It's just that to an observer like us, not the future observer, but the observer like us today, we would just have to say, oh, it just looks random to us. So that's an example of kind of what this kind of computational view of the second law has this consequence, that it is, the second law is the result of us being computationally bounded observers, observing this computational irreducible thing.
In time. And listeners, we've got an episode about retrocausation in this, and about the possibility in physics of time going backwards. Is there a compatibility with what you're talking about here, with the possibility that time can run symmetrically backwards at the same time?
Well, in our models, the progression of time is the doing of computation. So is it the case that you could take the state of the world at a particular time and sort of go in computationally unbounded way and reverse it? Yes, if you had unbounded computation, you could reverse it. Observers like us don't get to do that.
No.
Could we build a future technology where we do that? Well, actually, on a microscopic scale, people in recent times have been able to do that for individual molecules and so on. Will there be a future world? Would there be other kinds of observers who could routinely reverse, have the perception of the reversal of time? Not computationally bounded ones, but computationally unbounded observers. I don't know what they would be like. I don't think that's kind of the that's God versus humans type thing. It's kind of like it's hard to bridge that gap, so to speak, between the computationally bounded observers that we are and imagining a computationally unbounded observer. I think, a thing to say, by the way, about this notion of computationally bounded observers and observing kind of this sort of little slices of the Ruliad. The thing that to me is sort of an amazing realization is the second law of thermodynamics. People have thought for 150 years that it should be somehow derivable from other features of physics, that it shouldn't be something where the second law is kind of just a fact about nature. It should be something where you can derive it from properties of molecules. They have not thought that in the past about general relativity, theory of space-time, not thought that about quantum mechanics. The thing that's come out of our models is that actually all three of those theories are derivable. They're all things which, for observers like us, have to be that way, which is really to me, a very remarkable kind of, in terms of the philosophy of science, it's really kind of it's a rather dramatic thing, because I'd always thought that the laws of physics are just something we're dealt. It's like, here are the laws of physics, be happy, so to speak, rather than that the laws of physics are necessary for observers like us. And what we're seeing is that there's this sort of second law, general relativity, quantum mechanics, they're all coming from the same place. They're all actually the same phenomenon at some level of this interplay between computational boundedness of the observer and computational irreducibility of the underlying system. And that's, I mean, to me,
to see that entropy fits into that picture, again, for computational reasons, is really interesting. Now, some physicists here on the show...
Just to say for your listeners, maybe just say what entropy is, because it's sometimes a kind of a confusing concept. I mean, you can ask about a system. You say, I know certain things about the system, like I know every molecule in the system is in a box of this size. I don't know where the individual molecules are, but I know they all fit in this box. What entropy is, well, it's the logarithm of the number of states of a system consistent with certain constraints. So you know some general thing about a system, and then you're asking how many different microscopic states of the system are consistent with what I know. And that quantity, well, the logarithm of that quantity is entropy. And so when you say entropy increases, what you're saying is, given the things I know about the system as a computationally bounded observer, the system there tend to be more and more states of the system that are consistent with the things I know, but where my computationally bounded observation of the system can't distinguish between those different microscopic states. So that's why entropy increases, because given the constraints I have, it could be the case that the constraints I have are sufficient to constrain everything, and that I would immediately know, oh, the molecules have to be in this configuration or that configuration. But that's not true. Because of computational irreducibility, one ends up with a situation where the constraints I have are not sufficient to give me enough, to tell me enough that I can constrain those individual molecules. And so the number of effective states of the system consistent with what I know increases, therefore entropy increases. And that's kind of how that works out.
Oh, that's nice, because it's been defined many times on the show, but it's great to hear it in terms of computation and irreducibility. Thank you. Now, quick point here. Some physicists here on the show have argued that consciousness and perhaps we could say reason and computation too are themselves dystropic activities, sort of bringing order into a system and offsetting the tendency of thermodynamics towards chaos. And it reminds me of this sort of Hinduistic conception of prayer, or puja, as they call it, which for them, it's this method of keeping the cosmos from degenerating into chaos, from sort of flying off into randomness, to hold in balance this order and chaos balance that we see so beautifully in complexity theory. Is it possible to hold order in large systems without entropy leaking in? And could there be a possible universe in which ordered computation could evolve to eventually outweigh the entropy and thus contradict the second law of thermodynamics? Or is that just an impossible world?
For computationally unbounded observers, there isn't a second law of thermodynamics. In other words, the fact that we believe in the second law is a consequence of the fact that our minds are finite. One of the things to realize is, as our species progresses and we send out spacecraft to go further and further away and so on, we are expanding in physical space. The other thing that we're doing is expanding in Rulial Space. And the way we're doing that is by inventing new concepts. We have one point of view about the universe. As we invent new concepts, we're kind of getting different points of view about how the universe works. We're gradually expanding and kind of colonizing Rulial Space. And so one question is, the computationally bounded observer is stuck in the small region of Rulial Space. A computationally unbounded observer can be spread throughout Rulial space. And in a sense, it's sort of a paradoxical thing. You can say, let's imagine that we expand in Rulial space. We know more and more and more stuff. We can put more and more different kinds of ways of thinking about the universe. We can stuff them all into our minds. Well, in the extreme case, and we're incredibly far away from this, but I've done some little experiments where you can get some sense of how big human concepts are in the space of all possible concepts, and it is so embarrassingly tiny. It's kind of a little humbling. But in any case, one can start seeing that more explicitly, actually, in terms of AI and seeing what's possible there. But in any case, the thing to realize is, if we expand, and become sort of computationally unbounded in Rulial space, there's a big downer to that. The advantage is we get to spread out and know everything. The second law isn't an issue for us. All these kinds of things. There is, however, one little catch, which is, I think when we've sort of expanded throughout Rulial space, there is no coherent notion of existence for us. That is, the fact that we believe we exist. We have this single thread of experience, which seems to be pretty important to our perception of kind of consciousness, that we have a thread of experience and it's just a single thread. That doesn't work anymore. Then we don't end up being, in some sense, when we expand too far in Rulial space, we in some sense no longer coherently exist. And I think that has some resonance, actually, with some ideas from Eastern philosophy and so on. Although I have to say, I've my own. It's a difficult thing, I learn about different areas of science, and I work in different areas of science, and I slowly try to understand more things. But I have very much sort of spent my life in the kind of Western scientific tradition, so to speak, and I'm sort of gradually trying to understand a little bit more. Because it is kind of striking that a bunch of ideas, both from the pre-scientific period of philosophy, of the sort of theological period of philosophy, and ideas from Eastern philosophy, both seem to have a lot of resonance with the things that we are discovering, kind of using kind of the extension of Western science, so to speak.
I studied philosophy and religion, and I have to say I was extremely struck by how many of these ideas, particularly Buddhist ideas, actually are closely related. It reminds me of speaking with Carlo Rovelli, who on many, many occasions, while speaking about his relational interpretation of quantum mechanics, people kept telling him, you've got to read Arjuna, you've got to read Arjuna. And eventually, quite similar to the Buddha, actually, by the sort of third or fourth time that he was told to do this, he was like, well, I suppose I better do it then. And he went off and found that literally there was echoes in that Buddhist philosophy from more than 2,500 years ago of exactly what he was talking about regarding quantum mechanics. I don't think we can ignore the connection.
The challenge with all of that is, in a sense, there's a certain idea of progress in kind of Western thought and so on. And the idea of progress is a little different, I think, in other places.
They see it as cyclic. For example, in Indian cosmology, the universe expands and then contracts and then expands and then contracts, just to give you an example. But there are many such ideas of cyclic
right. But even at the level of conceptual development, I mean, one of the things that's happened in science, for example, and mathematics, is we built big towers. There's one concept, it builds on another concept, builds another concept, and so on. That notion of building very tall towers is something that happens when you can really formalize things, and when that, when every brick is very solid and you can keep on building. And so it's a somewhat different tradition when you're, which I don't understand as well, when you say this is a conclusion. And it's not so much, formalized building of one brick on top of another. So I think one of the things that's pretty interesting is can you take some of the intuitive conclusions, so to speak, and can you see how to kind of map them into this? Maybe you can also say some of this formalized development, you can say there's an intuition that you get from somewhere else that should help you guide that formalized development. And that's part of what's particularly interesting to me. I mean, it's also just fun when you find out that something that you just thought about for a few decades and finally figured out, it's kind of fun if you can go excavate and find out that 2,500 years ago somebody already figured that out. That feels
Yeah.
and it might have been lost for 2,500 years,
and it relates to my last question about reductionism, actually, Stephen, because another example of these ideas that keeps coming up is the idea of dependent origination in Buddhism, which is this idea that nothing can exist independently. It all exists in an eternal regress of relations to other things, and therefore all things are related. This unifying principle in Buddhism is the very sort of classic network thing, which I'm sure resonates with computer science, that basically nothing can exist independently. And of course, in science, these towers you're speaking about, in order to isolate into these little pockets of reducibility, we have to make a bunch of assumptions. And those assumptions are basically excluding things which are related. And therefore, immediately you're on the wrong track in some sense. And that's why I wanted to ask this important question about reductionism. Now, you're a self-confessed rationalist and computationalist. All scientific endeavor seems pointless if it remains subjective, if it can't be applied to your dream of sort of practically and unsubjectively describing the world and the encoded information in it. So my question is, how do you think about reductionism, materialist endeavors in physics to reduce phenomena to ever finer grained pixelation have kind of hit a wall where what appear to be fundamental subatomic particles, and they appear to be energy patterns and relations rather than actual space occupying particles anyway. Causality appears to be both upward and downward, and actually in all different network directions, as a neuroscientist put it, which I thought was beautiful. Anil Seth speaking about causation goes in all different directions. Space and time appear to be emergent properties in a computational background of Rulial possibilities, as you put it, in a matrix of almost infinite probabilistic quantum branches of history. Local realism has recently been experimentally proved to be false. Given all these updates in our scientific perspective relatively recently, do you agree with Princeton mathematician Nima Arkani Hamid, who has said reductionism is dead? I mean, if you would agree with that, how would you prefer to explain reality except in a reductionist way?
Well, I think that the thing that this idea that you can derive a lot from very little, that's kind of the hope of science. If to derive things in the world, you have to have the whole world, you didn't get anywhere. The leverage of science is from a little, you can say a lot. And I think that's that's really the essential phenomenon of reductionism is, can you put in a little and get a lot out? And for example, in the things we've done in our physics project, that's just spectacularly true. Very little goes in, a huge amount comes out. If you ask the question, I think a more limited view of reductionism, a more sort of mechanistic view of reductionism might not be in the right direction, partly because in our way of thinking about things, the observer is an important part of the story. And so if you say, can you just mechanistically grind down and find out everything is made of this particular thing and so on, the answer is no, that's not going to work. In the end, what you're going to find in our kind of what we've concluded you should find, you'll just find the Ruliad. And you'll say, well, that didn't tell me anything. That just told me it's all possible computations. I drilled down, I got to the end. We call the sort of atoms of existence EMES, like EMES. It's you drill it down and you've got a bunch of EMES, and you've got EMES and events that take place between these EMES, so you're done. Reductionism has worked, but yet reductionism's hollow at that level, because you're not really saying anything by saying that it's it's exciting to have managed to reach the end, but yet the end in and of itself tells you very little, because a lot of what you need to explain the world as we perceive it is things about us, which doesn't come with, knowing that we got to the end of reductionism isn't enough to give us science. So in a sense, if you say, is science reductionistic? My answer would be no. You can get to the end. It's a bunch of eames and events and the Ruliad and so on, but that's not going to give you the science that we perceive. To get the science that we perceive, you have to sort of go up again and start talking about what observers like us are like.
And the very nature of being an observer is reductionistic, because we're sort of, as you put it, we're bringing all of that in. We're assimilating all that into a single point of view that's actually useful to us, which is a reduction.
Yes, the different kind of reduction. I mean, I think the conceit of, yes, the fact that we can. So that I think there are two ways around to this. One is, how much do you get? How much do you have to put into the science to get a certain amount out? Another question is, you are taking the world as it is, and you are abstracting it for purposes of finite mind. And that's a little different, because you're throwing information away there. Sort of in the idea of, let's drill down and find out what's underneath, you want to know what makes everything we see. And that's as opposed to, let's take everything and just take our little slice out of it. These are both sort of, the word reduce you could use to describe both of these, but I think the action is a bit different in those two cases.
Absolutely. Well, Mr. Stephen Wolfram, you have been incredibly generous with your time. I do not quite know how to say thank you enough. And we shall meet up again online in order to discuss the possibility of having this all-important and I think quite timely conversation, not only about AI safety, but also about unleashing the extraordinary ability that AI can have and talking about ways that we could get there safely. And I think that's an extremely important conversation. It's been absolutely fascinating. Thank you so much, Stephen.
Thanks.